what Nico said. But today we are going to talk about smart contracts. I'm going to give you 2 lectures. One where I'm going to cover like the fundamentals, in case you are like Polkadot Maxi and you have never heard of smart contracts and only swear by Substrate. I'll go through the fundamentals. If you know everything about smart contracts already, don't worry. I will also take this opportunity to compare how a smart contract chain works versus like a Substrate chain. And on the next lecture, we will dive into like our own implementation of Frame smart contract module called Palette Revive. And yeah, that will be it for the day. I was supposed to give this lecture with my colleague Cyril, so we're gonna unfortunately skip a few lectures, but I'll be here to answer your questions if you have any. And as for tomorrow, we will do like a small hackathon. So you will use what you have learned today to work on some smart contracts on Polkadot, and whoever wants to present by the end of the day tomorrow will be able to present like its work. All right, so let's start with this presentation. So before I get into like all the nerdy details, it's important to start with the why. Why do we want contract on Polkadot? What is this technology good for? And why on our network, right? Why on Polkadot? To answer the first question, I like to show people like this small example of smart contract. So this example is an example of a crop insurance smart contract. There is an insurance company in the UK called Lemonade that has a blockchain foundation, and they have deployed this contract for a subsistence farmer in Kenya. And unfortunately, this farmer cannot subscribe to like classic insurance. It doesn't exist over there, or it doesn't apply to them because they're asking for very small coverage. And in insurance, in the insurance business, there is way too overhead, way too many counterparties to make this profitable for this company. But like this smart contract-based solution work, the way it works is that it's connected to like an oracle that provide like weather data information, and it feeds that to the blockchain, and the contract is able to like read this information, and in real time, if there is like a severe, weather condition event, like a drought or flooding, automatically send the payout to the farmer. So like the farmer doesn't have to, fill like tons of paperwork, doesn't have to wait for 6 months to receive their payment. They get their money straight away, right? So that's hopefully, a powerful example. And me demonstrates that, yes, maybe smart contract is like the future of finance. Maybe more so than, all the meme coins that you can find out there. And even if you think that it's not, a $1 billion idea, think about like the transparency of the system, right? If you are like a government organization, don't you want to invest into like this kind of scheme rather than private companies that is a bit opaque? I think the answer is pretty clear. Then the other reason we want to have this technology on Polkadot is so that we can leverage all the ecosystem of tool, infrastructure, and protocol that have been developed, specifically for the EVM ecosystem. So I'm talking about like, developer application like Hardhat or Remix that you might use tomorrow to like play with smart contracts from your browser and deploy smart contracts. But also like user-facing tool, right? Like wallets. If you want to onboard, the Ethereum community on Polkadot, you are better off telling them, to use like the wallet that they are familiar with, rather than, asking them to install something new. Then you have like a lot of infrastructure that has been designed specifically for the EVM. I'm talking about Block Explorer, like Etherscan, Chainlink, which is an oracle that provides like this kind of like real-world data feed that we saw in the previous example. And finally, because blockchain are write optimized, you also have like indexers like the Graph that provide you like rich API that you can use to provide like information to your dApp, get information from the chain on your dApp. And then finally, with this ecosystem come all of the the protocol that made the success of DeFi on Ethereum that we can also board on Polkadot if we have like a smart contract, an EVM compatible smart contract module. So here I'm talking about borrowing and lending protocol like Compound or Aave, or DEXs like Uniswap. If you have a question at any time, feel free to interrupt. All right, let's get into the how now. So I guess by now you are all blockchain experts, maybe more so than me. But for the context of this talk, it's enough to think of a blockchain as like state transition function that takes the state of the blockchain, the state from the state n of the blockchain, applies this transition function to like a batch of transaction, and output like the next state of the chain. So if we think of this state transition function as like a simple program, smart contract program, on Bitcoin, it will be fairly limited, right? It will just be a program that can transfer value from account A to account B. On Polkadot, like the logic of this smart contract will be much more elaborated, right? On Polkadot, you define your blockchain with substrate and frame lets you define palettes that each define some state and some transition function, transaction function that you can use to update that state. So this logic is much more complex, but still it's not permissionless, right? Not anybody can upload the runtime. To do that, you need to have like you need to make a root call to upgrade the runtime, and you can either do that if you have like sudo access, or you do that through OpenGov. So this brings us to what a smart contract chain is. A smart contract chain is essentially a chain with two types of accounts. You have what Ethereum call externally owned accounts, like Alice and Bob, that are governed by a private key that lets them sign transaction and interact with the system. And you have smart contract accounts that are not governed by like a private key, but by the code that you upload on the chain and define their behavior. So here you can still make transaction, from Alice to Bob by using Bob as like the destination, but you can also call into a contract by specifying their address and pass them some input so that they can execute and update like their internal state. So if we zoom out on the system, it looks the flow looks pretty much like this. So you start with some source code. On Ethereum, you will use Solidity. On Polkadot, as you will see later, you can either use Solidity, but you can also use Rust directly, or like a framework like Int that use Rust under the hood. You will compile this source code, and it will generate like some bytecode ready to be uploaded on chain, and some ABI that defines the list of input and output that your smart contract expose. This together with your private key that you submit transaction to the chain. So when you submit a transaction, you will use like the JSON RPC API. So we'll go back to that in a bit. To send your transaction to the node. So the node will get your transaction, gossip it over the network. Eventually, it will be picked up by a block author that will execute this transaction. And when it do so, it will like load the code from the storage, or take it from the call data if you are deploying a new contract, and pass it to the virtual machine. The virtual machine will execute the code instruction per instruction, and as a result, will update like its state, like the state of the contract. So if we look at like a fairly primitive bytecode, here we have like some EVM bytecode. So EVM is like a stack machine. So here we are pushing the value 10 on the stack, then the value 20, then we are calling the add instruction to add these two values together. And then if we want to store this this result into like the memory of the VM, we first push like the offset of the memory index. So here 0, and then we call the mstore instruction to store that into memory. Then if we want to return this value, we push first the size of the output. So here it's like just 32-byte uint value. Push like the offset of the memory address. So here 0, and then call the return instruction. And so this would return the the output. So that's kind of a limited like set of instructions that I show you. On EVM, you have access to much more instruction. So a typical instruction set will look like this. So you have like basic instruction, arithmetic, bitwise, and memory and stack instruction, and then control flow to like jump into different part of the code. Then you have like instructions that are specific to contracts. So you can call another contract to add a new contract on the call stack. You can interact with the host to like store or read data from the chain or emit some logs. And then you have instructions that are related to like the current context, like the block and the transaction that is being executed. So usually you will not write the bytecode by hand. You will rely on some source code language. The most popular one on Ethereum is Solidity. So if you have never heard, if you have never seen Solidity code before, it looks pretty much like this. So here we have a simple piggy bank smart contract. It defines some state, some fields. In that case, just one, the owner. And here it's also defined as immutable. It means that it can only be set at deploy time. So when you deploy the contract, you run the code of the constructor. So here it's simply setting the owner to the sender of the transaction. Then typically in contracts, you will find a read-only function that lets you like read the state of the smart contract. Here I have like a simple like get balance. I have a simple get balance function that is simply returning like the balance of the contract account. So contract, just like other like regular accounts, carry a balance and a nonce, and you can access this from the address. Then if you want to mutate like the state of the blockchain, you can have like write operation. So if you want to deposit some funds to a contract, you have to tag your function with like the payable keyword, so that you can transfer some value to like the contract account. Then we have like this withdraw function that also mutate like the state of the contract. So here it's pretty simple. It starts by checking that the owner is like the message sender. Check that you have enough amount on the contract that you can withdraw, and then call the sender to send this like withdraw amount. All right. Let's look at some of the core features of smart contracts. So first of all, there is the notion of gas. If you can, you might tell me that if you can execute any kind of arbitrary code, what prevents you from running like, for example, like a while true loop that will DOS like the blockchain? The answer is that you cannot do that because every instruction that you execute in your smart contract is metered. And you have to pass your transaction, like an amount of gas that you're willing to spend. And on top of that, like the amount of gas that goes into the block is limited, right? So you cannot execute like a while loop that runs forever. At some point, it will throw like an out of gas error. A bit small. On the EVM, the way like the VM works is pretty much like this. So it starts fetching like the next opcode that it needs to execute. Look up the cost of this opcode. Deduce that from your gas meter. If you have enough gas left, it will continue the execution, execute this opcode and continue the execution. If not, it will just throw an out of gas error. So either the contract, throw an out of gas error, trap for some reason, or run until completion. If we compare that to how we do things in Frame things look a bit different. In Frame, when you define dispatchable, you tag them with this pallet weight attribute here. And this pallet weight attribute here define the pre-dispatch weight that needs to be taken from your account so that you can execute this function. So here, for example, we have like the set metadata function from pallet asset. It lets you define a symbol, a name, a symbol, and a decimals amount for your asset. And you can see that this weight function here is a function of the length of the name and the length of the symbol. What that means is that the more data you're going to write on chain, basically, the more expensive this operation is going to cost you. The more weight this operation is going to cost, and weight translates to transaction fees. So if we compare like both systems side by side, so the execution model is metered on the EVM, on the smart contract, whereas on Substrate you have like this pre-dispatch weight that you use to take the fees from the users, and you do that before like the execution. So the cost is dynamic on EVM. It depends on like what code you are executing, whereas on Substrate it's like static, right? You know exactly what code you are going to execute, right? So you can determine pre-dispatch how much your code is going to cost. So of course it comes with like some runtime overhead for smart contracts because you have to run this tight loop and do like this bookkeeping of the gas. So it costs some compute time. Whereas on Substrate, things are more optimized, right? You just subtract the fees once, and then you run the code without any kind of overhead. On the flip side, when it comes to flexibility, like developer experience, it's much easier to write a contract, right? Because like this gas accounting is baked into the system. You have to think about gas because you want to make your contract as cheap as possible, but you don't have to write any kind of benchmark. You've done some assignment, I guess. So if you become like a runtime developer, you will find out that you spend most of your time writing benchmark. It's maybe like the most complex task of running a safe runtime. All right. Then another characteristic of smart contract is that they're like highly composable, right? They all define some API that you can use to communicate with these contracts. Think about, for example, like a flow on Aave where you contract a flash loan, you execute like some smart contracts that use this loan, and then you refund the loan at the end of the transaction, right? This complex flow can be executed because like all these smart contracts are like composable with one another. So you have 3 types of call that you can make from our contract. We can see them in action actually. It's more. But first of all, like one thing to notice is that this complex chain of contract interaction always start from always initiated by an externally owned account, right? So Alice here is calling into contract A. You can think as smart contract as like dormant programs that are on the chain and that are only triggered by some transaction. So here we have the EOA that call contract A. So contract A is going to be put on the call stack, and it's contract and storage is going to be loaded. You're going to be able to like mutate like this storage. And at some point here, like contract A is calling contract B. So B is going to be pushed to the call stack. Its code and storage is going to be loaded. And because it's a regular call, you can act on the state of B. You can mutate like this data field, for example. Then the last type of call is delegate call. So like B is calling contract C, and it is making a delegate call to like the function C. And when you make a delegate call, you execute like the contract C, but in the context of B, right? So like the code of contract C is going to be loaded, but the storage that you can act upon is like the storage of the caller. So storage B. All right. Another topic, important topic, is like the concept of precompiled contracts. So you have 2 types of contracts like you can execute on a smart contract chain. You have the contract that people deploy and are executed through the VM. And you have like contracts that are baked into your client. We call that precompiled contracts. They live at predefined address and they execute natively, in the client. Initially, they were created in Ethereum, like because for example, executing a hashing function is like compute intense, and it will be very slow and very gas intensive to like do like a SHA-3 of some bytecode in the VM. So instead, you do that directly natively in the client, and you can have like much cheaper cost. For us, it's very important as well because in Polkadot we have like it's not only we don't have only like a smart contract chain, but we have like a runtime substrate chain that exposes like different palettes. And through these precompiles, we can expose basically all of the functionality of the chain behind like a Solidity interface. So for example, if you are like on Polkadot and you want to access XCM or palette asset or governance or staking, eventually when we have precompiled for all of these palettes, you will be able to do so. All right. Another characteristic of smart contract is that the code you put on chain is immutable. So think about like our insurance smart contract, right? If you were able to like update it anytime, it would be like a pretty weak insurance system, right? So it doesn't mean that you cannot upgrade a smart contract, but if you do so, it's going to be clearly exposed in your code, right? One way to do that in smart contract is to use like the proxy pattern. How it works is that you have a main contract that basically delegate all of its code to like another contract, right? And you can update like this implementation address, either and you can define how like this address can be updated. You can say that maybe like only the owner of the smart contract can update this address and change like the version to version 1 to version 2, or maybe it's only done through some kind of DAO vote. If we compare that to Substrate, on Substrate you can also like upgrade the logic of the runtime through like a runtime upgrade, right? And this can be done similarly either through sudo if you have like a chain that has the sudo palette, or through on-chain governance, which is the case for every chain that exists on Polkadot. And finally, if you look at the overhead of that, there is some gas overhead for smart contracts because you have to load the first contract and then the delegate contract. So loading these two contracts costs you some gas. Whereas on Substrate, everything is optimized, right? Once you have upgraded your chain, like the new code lives in storage, and that's the one you are executing. All right. Another point, which is I guess more global to Web3, but that also applies to writing smart contract, is that you have to pay close attention to like the security. For that reason, most of the time when you write a smart contract, you prefer to use like some well-established smart contract library like OpenZeppelin ERC20 contracts, rather than rolling out your own contract. And another thing is that when you write your code, you have to be aware of some of the bug that you can have, right? And make sure it's like bug-free. Like one of these famous bugs that I'm sure you have heard of is like the reentrancy bug from the DAO hack. That split the Ethereum ecosystem into Ethereum Classic and the Ethereum that we use. So like the way this DAO hack happened is that you have like this vulnerable or like DAO contract that has like a storage that defines some accounting between addresses and some balances that have been deposited. And you have like this withdraw function that lets you like withdraw your funds. And what this function is doing is that it's first taking like the balance of the sender, then it's calling the sender to transfer this value, and then finally it's like updating its internal accounting, the balances field. And so if you execute this contract from like a regular account, it will work perfectly. But if you execute this contract from like an attacker contract, this line here will execute like the fallback function of the contract. And this fallback function will take the value, but we'll be able to execute any kind of arbitrary code, right? And why it's called reentrancy is because you're going to recurse into this withdraw function and drain the fund of the DAO. Because like the updating of the field is only done at the end instead of at the beginning. So we can actually like execute like this code, and I can make you a small demo. So that I can show you as well some of the debug API that are available on the JSON RPC server of our EVM implementation. So maybe it's too small. So here, let's see. I have that same contract that I showed you in the slide. We have the DAO contract here that have a get balance function, deposit function to deposit some funds, and then it has like this this withdraw function here. And what we're going to do is we're going to deploy this contract and also deploy this attacker contract here. And what this attacker contract is going to do is it's going to, first it's going to define how many times it want to recurse when it's like trying to drain the funds. And then we're going to execute like its attack function, right? What this attack function is going to do is that it's first going to deposit some value, because you need to deposit some value initially so you can withdraw the funds. And then it's going to call like the withdraw function of the DAO contract, right? And when the DAO is going to call the attacker to send the value, it's actually going to call this receive function here. And what this receive function is doing here is that it's checking that we have recursed less than the amount of time that we have specified, and call again into the withdraw function over and over until we've drained enough times. All right, so the first thing I need to do is need to build a contract, but I've done that already, and I have a small script here that is going to deploy our contract. Right, it's going to deploy the DAO, and it's also going to fund the DAO with like some money, and then it's going to deploy the attacker. And now what I can do before I execute the transaction is I can look. Actually, look at how I can look at the I can dry run the attack call and show you like the traces of the contract. Shit. So I'm like, here I'm basically just executing the tracing API where I'm driving this call and I'm piping it to JLS that show me the JSON in this tree program. And I've replaced, to make it more readable, I've replaced all the address by caller and attacker. So here we see that we are calling from from Alice or whatever account the attacker contract, right? And we are calling the attack function, right? So it's a regular call, and you can see that the first thing that it's doing is that it's reading the balance, right? So it's doing a static call to the DAO contract. So from the attacker to the DAO contract to read the balance, right? And then first it's depositing some value. So it's calling the DAO and calling the deposit function. And then finally, it's going to call the withdraw function, right? And then here we see that we're going to see like the reentrancy in action. So you can see that the DAO is going to call back into the attacker, right? And then this is happening over and over again, right? So up until like the amount of time we've specified. So this way we are like kind of draining the fund of the DAO. Now I can show you. So yeah, if I show you this in action now, and I run the transaction in loop, you can see that like the fund of the attacker are increasing, and it's draining the DAO, even though we started with like a balance of 1, right? And that's pretty much what happened on the DAO hack. Actually, we don't need to see it until the end. So to execute this little program, I use like the JSON RPC API of Ethereum. So stand for remote procedure call, JSON being like the encoding format. If you inspect like the call from your MetaMask in your browser, you will see that the most popular API are the following one. So isCall is like the API you use to make a read-only action to the chain, right? You will pass like the contract you want to target and the function that you want to use. Then if you want to, do like a write operation, you need to submit a transaction. But first of all, you need to estimate the gas that your transaction is going to cost. So you will call is estimate gas. This will return you like a gas value. You will take this gas value, put it inside your transaction, encode your transaction and sign it, and submit like the raw payload with is sun raw transaction. And then finally to get like this, whether or not like the transaction was successfully executed, you will pull like this is get transaction receipt endpoint. That will tell you eventually that the transaction was executed and whether or not it was successful, and show you some of the logs as well. On the substrate, like this equivalent of these functions are the state call API that lets you like tap into any runtime API defined by your palettes. So you will pass your palette name and the runtime API of your palette that you want to call, as well as like the scale encoded parameters that you want to use. And to submit a transaction on a substrate chain, you use like this author submit extrinsic endpoint. So if I wanted to send a transaction to Western, which is our testnet, I could use curl like this. And you see that here I'm specifying that I'm using JSON RPC. You need to specify an ID because you can batch transactions, and each transaction defines its own ID. You specify the method. Here we are calling is_sun raw transaction, and you encode like the encoded payload goes in the parameters here. If we want to understand what kind of payload we have, we can use like this handy tool from the Foundry project, which is a popular like dev tool in the Ethereum ecosystem. You can call cast decode tx, pass like your payload, and you will see that you will be able to like decode like the transaction. So this transaction is actually encoded using ORLP, recursive length prefix algorithm. So it's different from substrate where we use scale to encode everything. The first byte here is actually not part of the encoding. It just specifies like the type of the transaction. So every new hard fork on Ethereum can define a new transaction type to enrich the transaction format. And so in this transaction, we have this type that we just defined. And then we find like the chain ID. So each EVM chain defines a chain ID. This is used to avoid replay attacks, right? So that if I submit a transaction on Ethereum, you cannot replay it on Polkadot or Base or some other chains, right? Because they all check that the chain ID is set to their chain. Then you have a nonce. Similarly, nonce is to avoid like a replay attack. You can only execute a transaction with the current nonce, and then it's incremented after each transaction. Otherwise, you would be able to replay the same transaction over and over, and that would be pretty bad. Then you have like the gas values that you have estimated and that you have encoded here in hexadecimal format. This specific type of transaction is from the London fork, and instead of defining a gas price, it's defined a priority fee and a max fee. So you can define a priority fee to boost to pay a bit more and boost like the transaction so that it's executed before others. Then this transaction is actually like in a USDC transfer, so it's not passing any value, so it's set to 0. If I wanted to pass some value to the contract, I will be able to pass it here otherwise. some input that is encoded, and ABI encoded, we'll see how later. And then like this last 4 fields are part of the elliptic curve signature of the transaction. You'll notice here that there is no from field, right? That's because you can actually like recover the signer from the signature. All right, now if we look at how like this input is encoded, let's try to understand how it's built. The first 4 bytes here at the top define like the selector of the function that you want to target, right? So here we know that it's USDC transfer. So if I was the way it's so these 4 bytes are actually like the 4 bytes of the KCAC hash of the signature of the code, right? So if I call cast KCAC, pass the signature, and take the the first 4 bytes, including like the 0x, I can recover like this prefix here. There's actually like a handy function as well, a handy command in cat as well that's called 4-byte decode. You just pass the input and it's able to tell you like what is the signature, and it's able to decode the input. It can do that because it has access to like a web service where all of the popular smart contracts are stored, and it's able to do like the reverse lookup from the hash to the signature. Now, as for the parameter themselves, so everything in the EVM is encoded using like the ABI specification, whether you are sending the data from the RPC or you are calling another contract in the VM. The way it works is, so for example, if we have a call here that takes a true Boolean, a string hello, and some address, the Boolean is encoded first, and you'll see that everything is padded on 32 bytes. So here we have the Boolean true, so it's like the 1 padded by 31 0. Then we have a string. So a string is a dynamic type. So we don't store it in line. We first store the offset of where the data is stored. And then here at index 60, we have the first length of the string, and then the string itself. And then finally, the last parameter here is the address. And so the address is a fixed type. So it's encoded on 32 bytes. It's only 20 bytes long, so it's padded with 12 0. All right. So in this second lecture, I'm going to talk about Palette Revive, which is our frame module where we have implemented like smart contract. So before I start talking about the palette itself, for those of you that haven't done the protocol track, just a reminder. So a substrate node is essentially composed of 2 parts. You have the client here at the bottom that is in charge of executing all of the general like purpose like blockchain tasks, such as handling the JSON RPC call, managing the storage, gossiping the transaction over the peer-to-peer network, storing the transaction in the transaction pool, and so on. And at the top, you have the runtime, which is compiled in WebAssembly, and whose code live on the blockchain. And our palette here, Palette Revive, lives inside the runtime among like some other palettes that it depends on. So we have a Palette Revive, which is like a smart contract module, but what we want is also like a compatibility layer so that you can call our module from an Ethereum wallet, right? From like a wallet like MetaMask. And for that, we have developed a small proxy, an ETH-RPC proxy that implement like the Ethereum JSON RPC spec. This small proxy usually is co-located with the node, and it's talking to the node through like the substrate API, right? It's just like relaying like the queries to the node. On top of that, it's it has like a small off-chain database to handle some mapping between like the Ethereum world and the substrate world. You have different design decisions that you can make when you create like this compatibility layer. You might have heard of Frontier, which is also like another module that brings Ethereum compatibility. They have a different approach. They have like the JSON API baked inside the client. We decided to go with like a proxy approach for a few reasons. One of them is that there are like multiple implementation of the substrate node. I think you have like a C++ implementation on top of like the official parity REST client. So if we were like adding JSON, Ethereum JSON RPC API to the node, we would have to do it in every single implementation. So instead of that, this API live in the proxy. The second reason is that it let us we are still early stage, so it let us iterate fast on the JSON RPC API, and we don't have to redeploy like the node client every time we make an update. The only thing we need to do is basically update palette revive, upgrade the runtime, and push some updates to the ETH RPC proxy binary. So if we look at the flow from the wallet to the node, it looks pretty much like this. You send a transaction from your MetaMask or your favorite like Ethereum wallet. This transaction will be submitted to like our ETH RPC proxy, and the ETH RPC proxy will simply package that up inside a substrate call. Right? Every transaction in substrate needs to be an instance of a call of a pallet, and so here it's no different. And for that, we have like a specific call called ETH transact that simply like take like this raw bytes from the transaction and submit it to the node. You have two ways to submit a transaction in Substrate. You have three types of transaction in Substrate, right? You can have inherent, which are like transactions that are created by the block author itself. Then you can have like signed transaction and unsigned transaction. Here we are like submitting the transaction as an unsigned extrinsic, because like the signature itself is part of the Ethereum payload. And so on the node in Substrate, there is a special trait called checkable that lets you convert like this unchecked extrinsic from the outside world into like a checked extrinsic with like an account ID associated to it, like and a call that you want to dispatch. So the way we do that is that we implement this checkable trait, and we check like the type of the call. If the type of the call match is transact, we decode the transaction and extract the caller from the signature. So the signature can be used to recover the address of the caller. And then we route that to palette revive. Palette revive has like a call and instantiate that you can use to either call or instantiate the contract. So we route that to palette revive. All right, let's take a look at our palette. So if usually, if you're familiar with the palette, like a good place to start is to look at the configuration. The configuration of palette revive is pretty long. That's because we need to expose like a lot of functionality of the chain to smart contracts, right? So we manipulate currency in contracts. So we have like this currency type. All of these types, you will find them in other palettes usually. You have like runtime events because we want to be able to like submit events from a contract. What else do we have? You have things like, I won't go through everything, but you have things like time and find author, because a contract needs to be able to access the Coinbase, like the block author, but also like like the current timestamp. I'll go into the detail of some of this property later, but if you scroll down, you will find then types that are specific to our palette. So for example, I think I mentioned that earlier, you can define the upload origin and the instantiate origin, right? So if you want to have like smart contract on your chain, but only allow like maybe a multi-sig or a pseudo user to deploy your contracts, you can do that. You can also decide to like disable like deploying contracts altogether, and simply have pallet revive inside your runtime so that you can expose everything in your chain through like this EVM interface, right? So that you can build that using mainstream JavaScript library instead of using PAPI or Polkadot.js. And then a little bit down below, you have more tabs that are specific to the Ethereum compatibility layer. So you need to define a chain ID, as we discussed earlier, to avoid like the replay attack. And then you have other types here that I will discuss in more detail later. The second place usually you inspect when you look at the palette in Frame are the list of dispatchables, the list of transaction type that you can submit to the chain. The main one in pallet revive is like this call function that lets you like call a contract. So this function here take a destination, so like an address, H160 address, like an Ethereum address, some values that you want to transfer, a gas limit expressed in weight, and some storage limits expressed in the native balance, as well as some data that you want to pass to like the contract call. If you have done the protocol track, you'll notice that here, like the weight function is a bit different than the usual one. So the way it's defined is that like the pre-dispatch weight of this dispatchable is defined by this base weight here, call, plus any weight that you have defined as a parameter here. So in a way, like the pre-dispatch weight here is dynamic, right? It's based on the gas limit, which is like the gas that you have estimated with your dry run. Another thing to notice here is that usually frame palette return just like a dispatch result. This call here return a dispatch result with post info. That's because you might have provided too much gas, and we want to refund you like the excess of gas that you haven't consumed, right? And that's why we have like these two variants in frame, so that you can get refunded if you haven't used all the gas. So the other list of dispatchable we have in the palette are listed here. So you can upload some code on the chain with like the upload code call. You can instantiate a contract whose code has previously been uploaded by picking its hash. You can do the two operations together by calling instantiate with code. Then we have the call function that we have just seen before. And finally, to bridge like the address type that we have in Substrate and the 20-byte address type that you have in Ethereum, we have like this map account that I will discuss a bit more later. Map and map. All right. Now, if we look at how the palette works, the first things, it's a bit small maybe, but like the first thing that you notice is that we have a PVM interpreter inside the palette. So we are executing not EVM bytecode, but we are executing PolkaVM bytecode. The reason we are using PolkaVM and not EVM bytecode is because we want to innovate, right? And at some point, we want to be able to just-in-time compile this code, right? EVM, as we have seen earlier, it's call stack virtual machine, right? And not a register-based virtual machine, right? Your computer uses register and not like, so your register is using a register, so it's easier to convert some code that is register-based rather than stack-based. EVM is also using 32-byte words, right? Whereas your computer, whether it's ARM or x86, is using 64 bits register. And finally, EVM is also using big endianness instead of like little endianness. So all that makes this EVM bytecode quite complex to translate into machine code, right? On the flip side, with PVM is like based on RISC-V, and so it's a register-based machine. We use like the 64 bits version of it, and we have designed PVM in a way that you have less register in the VM that you have on your physical computer. So that means that translating the bytecode into a native instruction can be done in linear time. If you try to translate some WADM code or something else, it's going to be an NP hard problem, right? So it's going to be unbounded. And someone could craft a contract that make it super expensive to convert to native code. So you cannot use that in the context of a blockchain, right? We compile the runtime with wasm time into machine code, but we do that ahead of time, right? Here, when you execute a contract, you need to be like resources are scarce, so you need to do it, and you need to do it fast if you want to execute the code on the machine. Yeah. That being said, it turns out that so you can use Solidity and compile that into PBA bytecode. We have like a compiler that the team is working on called Result-C that you will be using if you use our own fork of Remix or other tools tomorrow when you work on the hackathon. But we only support with Result-C the latest version of Solidity, right? And we want to be able to port all of the Ethereum application that have been created on Ethereum on Polkadot. And so for that reason, and because there are like some quirks on the oldest version that we don't support, we decided to add as well an EVM backend. So this is being merged as I'm speaking, but what that means is that ultimately we will have multiple backends to execute your contract. You will be able to submit EVM bytecode and execute it through like the EVM interpreter that we are adding to Palette Revive, or execute PVM bytecode. And for PVM bytecode, you will either have the interpreter, or at the end of the year when we get time to work on it, we will work on the just-in-time compiler, and you will be able to like either interpret the code or run it natively on the machine. So that means that you will be able to execute the contract at the speed of the runtime. For some cases, we still want to have the interpreter, because for like a small contract, it's actually like easier to interpret it in place rather than paying the upfront cost of like compiling the contract and then executing this contract in native code. All right. If you look at the palette, we have a proc macro called define env that we use to have expose all the host function to your contracts. This proc macro basically takes care of like calling all of these functions that you define here. So fetch storage, read storage, accessing like the block, stuff like that. It takes care of like setting up the register so that it can call, so that it can understand like the parameters that are sent by the virtual machine. On the flip side, if you define a contract, you can actually define a contract in Rust code, and you need to have access to like the foreign functions that are exposed by our palettes. And we have designed for that a small module called Palette Revive UAPI that you can use to call into like the different host function of the palette. And this macro will take care of like, again, all the dispatching logic of setting up the register for you and reading like the output register. So I can show you a quick example of this. So here I have a small project, Rust contract template that you can clone from GitHub. And it's actually defining a simple contract using like this low-level API in Rust. So usually when you build a contract, you will want to use Solidity because it's more high level. But a little bit like when you work on a program in Python and you want to have some performance boost and build some library in C, you can do like the same thing here, right? You can build like your top logic in Solidity, and if you need to crunch some numbers of like more performances, you can build your contract directly in Rust, where you have access to like a richer like type system and can define for example, like integer that are not on 32 bytes, but on 4 bytes and so on. So this simple example here is actually like the Fibonacci suite. It's a bit hard to. And I can, so it has, yeah. So it exposed 2 entry points. Wait, the first one. So you have like this entry point here, deploy, that is actually like a, oops. That is actually like a empty function that is used when the contract is going to be deployed. And then when the contract is being called, it's going to run this call function here. And this call function here, what it's doing is that it's first it's like decoding the input. I can show you later how it's done. Then it's going to call like the Fibonacci function that we have defined below. So it's just like a simple function. As you can see here, we are just using like U32. So it's more efficient to execute this here than if you were like doing that in Solidity, where it would use like 32 bytes integers. And then it's encoding the output and calling the API return value to return that to the caller. So first you decode the output, you execute your call, and you return the output to the caller. To decode the input, you can do it like the old-fashioned way, like I showed you like in the previous talk. So you know that this function will be defined with this ABI. So it will take a uint and return a uint, right? So you basically know that it's like the data that the contract is going to receive is like the 4-byte selectors, and then this integer of the Fibonacci suite like encoded on 32 bytes, right? So you can do like this if you want to build something very low level. You can just like use like this low level API and create like a buffer manually and decode it yourself. If you want a slightly more high level way of doing this, you can use Alloy, which is a crate on Rust that lets you parse some Solidity file or some Solidity code. So here we have the interface that this contract is implementing here. And it will give you access to, it will generate some structs for you with like a function to like decode and encode like the inputs and outputs. So here we just, first we need to get like the length of the data. Then we need to copy this data into a vec. And then we can just call ABI decode on the class, on the struct that has been generated here. If you do that, you will need to, I did that yesterday actually. You will need to, because it's like quite a level and we don't have like an allocator in Pilot Revive, you will need to provide your own allocator. If you want to build your contract in Rust with like a higher level API, you can use Ink, that I guess will do all of this kind of thing for you behind the scene. So I will use the README to execute this. You can go through the README to see how. So when you compile this code, and then you call Polkadot tool to like link it into like to link the ELF file into like Polkadot VM bytecode. So I think I've done that already. So this will generate the bytecode, and then you can use cast again that I showed you earlier. This command here to call the contract. So this is deploying the contract at the, let's see. So it's deploying the contract at some address, at this address here. But because I'm lazy, I'm going to copy this code here. That we deploy the contract, but like, set the address in this Rust address variable. And then you can call this contract. and get the result of calling Fibonacci with like the integer 4. And actually, if you want to play with this example later, you can also like deploy the same code in Solidity, and you'll see that at some point, if you run the same code in Solidity, it will run out of gas, but you'll be able to like compute like the Fibonacci suite up to like a bigger number when you deploy like this first code. Just because like this code is more low level, it's using like U32 integers and can can do more. The nice thing is that like these contracts, from the point of view of the VM, they are equivalent, right? So you can call one Rust contract from a Solidity contract. At the end of the day, all of that is just ABI, EVM ABI bytecode that you can consume from any contracts. Yeah, let's go back to the slide. All right. Another thing that we mentioned earlier are precompile. And as I said, in the context of a substrate chain, it's important because through precompile, you can expose all of the different palettes that exist on your chain. And for that, we have like a trait in the palette that lets you do that. So when you define a precompile, so you have like a few associated types. So you have a T, like everything in substrate, that is like the type of your runtime. And then you have an interface, like a Solidity interface, that define like the shape of your input. Then you have a matcher that defines where your precompile is going to live. At which address you can find this precompile. So like this address matcher can match on one address or like a range of addresses. And finally, you have like the entry point here, call, that receives like the address that was matched, the input, like the Solidity interface input, and has access to like the host function through like the X trait that exposes all the function of the palette that you can use in your code. So if we look at a simplified version of how we implemented like the palette asset precompile, so we have implemented like the IRC20 interface. So the way you build that, and that will be kind of like the same pattern for all of the precompile that you design. You first have like some Solidity interface that you want to implement. And so you can use, again, like this handy macro that I showed you earlier from Alloy that takes some Solidity code. You can either pass like some Solidity code inline or just reference a file that exists in your project. So here we have like all the function of the IRC20 contract. Then you define your precompile struct. So here IRC20 generic over the runtime, and then you implement the what is that? And then you implement the precompile trait. So here we are implementing a precompile for palette assets. So we need to specify that the runtime is something that implements palette revive, but also palette assets. We specify that the interface is like this IRC20 calls that was generated by the macro above. And then we specify where, at which address like this precompile is going to live. So on this example here, I'm using like the prefix address matcher. So that means that every addresses that use this pattern are going to be matched, right? So you can have anything encoded in the first byte here, and then the rest must match like this pattern. And so finally, when you implement this precompile, so you have like the call function. The first thing you want to do is extract the asset ID from the address. So you will use like these 4 first bytes to decode like the asset ID. Once you have the asset ID, you just basically match on the input. So the input is going to be one of the call of your interface, right? Transfer, total supply, balance of, and so on. And in the implementation here, you will simply call into your palette one of the public functions that is exposed by your palette to implement this. So if you look at Asset Hub, where we are deploying Palette Revive. You will see like that the precompiles type is defined as such. It's a bit more complex than in the example that I showed you, because you have actually like 3 instances of Palette assets on Asset Hub. You have trusted back asset, pooled asset, and you have also like foreign assets that we don't support right now, because you cannot, you cannot encode like the ID of like the XCM location inside the address. So we will need to implement it using some kind of stateful storage later on. And I think Francisco, that maybe here, yeah, implemented like the XCM precompile. So through the XCM precompile, I think you can send XCM code and maybe do other stuff. Yeah, that's it. Okay. So yeah, for example, on Asset Hub in Polkadot, you have like the USDC token that is defined at index 1337, so 0x539 in hexadecimal. So if you use the type definition that we've seen earlier, it means that the USDC contract, precompiled contract, live at this address. So if you want to send me some USDC, I haven't put my address here, but you can call cast, specify the address of the contract, the signature of a ERC20 transfer, so transfer an address and an amount, specify my address and like the amount you want to send me. All right. Now I just want to list a few differences that exist between and we had to work with the differences between Substrate and Ethereum that we had to deal with in the palette that might be almost transparent for you when you use the Ethereum compatibility layer, but that is always good to be aware of. The first thing is that on Ethereum, like the transaction hash, so like the hash of the transaction that you get when you send a raw transaction, is a unique identifier, right? So if you have used Ethereum before or the EVM chain, you've noticed that the link that your wallet gives you to inspect your transaction is ethscan.io if you're using ethscan/tx/the transaction hash. On Polkadot, the hash is not unique, so if you usually the link that you will be given is subscan.io/extrinsic/the block number and the transaction index. And why it's not unique? It's because on Substrate there's the notion of existential deposit, and if your account, like the value of your account goes below the existential deposit, your account will be ripped. So in this, in this little example, if you have an account A that transfers all of its dots, so 5 dots to account B, as the result, A will be ripped, right? So if in the same block, B is transferring 7 dots to A will be recreated again with the same nodes, right? And that means then when A submits 5 dots again to B, both the first and the last transaction will have the same hash. So for that reason, we have like a small off-chain database in the ETHRP proxy where we map transaction hash to block index and transaction number, so that we can fetch like the information from the Substrate node. So I mentioned existential deposits. So again, that's something that doesn't exist on Ethereum. And that means that if I send some value to a new account in EVM, I'm expecting this account to receive like the full value, right? And so what that means is that we need to send actually like the amount that you specified plus the existential deposit when we do that. The existential deposit will be charged on the transaction fee so that it's transparent to the contract. All right. Another difference is that on Ethereum, there is a concept of init code and runtime code. So the code that you deploy is not the code that lives on chain. When you deploy a contract, it's going to run the constructor that return the runtime code on Ethereum, which itself stored on chain, right? So the compiler basically will return like the code of your contract with like the constructor code removed, and it will inline all the immutable storage that you set in the constructor. Yeah, if you use Sol-C, you can actually see that in action. If you compile like a dummy contract, you can ask for the binary and the bin and the bin runtime, and you will see that the bin runtime is actually like a subset of the binary that you deploy. So in PVM, things are a bit different. We only have like one code that we deploy, and as you have seen maybe in the previous Rust example, you have two entry points on this bytecode. You have like the constructor and and the call that you use once the code is deployed. The immutable variables that are baked inside the runtime code in EVM are, in our case, like just stored in a map storage, and yeah, so it works a bit differently. It means that it's much more space efficient, right? If you think about, I mean, on Ethereum, all of these ERC token that you deploy, they end up all creating like some new code storage on the chain, right? So it's kind of bloating the the state of the chain, right? In our case, if you deploy 1,000 ERC contracts, there will just be like one version of the code, right? And all these contracts we just reference like the same code hash. And for this reason, because when you deploy a new contract, you kind of like increment like a ref count on the code hash. We have like this extra charge, extra deposit that we take from you, so that you don't try to game the system and lock the fund of someone else, right? So when you deploy a new instance of an existing contract, you will be charged a percentage of like the initial deposit that the person that uploaded the code paid. All right. One other difference is that the number of decimals is different on all of these chains, right? So on Ethereum, one ETH is defined on 18 digits. On its 10 power of the 18, whereas on Kusama and Polkadot, like the smallest unit is called plank, and it's 10 power of 12 plank on Kusama and 10 power of 10 on Polkadot. In theory, RPC are configurable, and you can specify like the decimal numbers of your chain. In practice, everybody is using 18 digits, both from the RPC, but also like JavaScript library and like contracts that are deployed expect your value to be manipulated on 18 digits. So for that reason, we have like this type native to ETH ratio that basically scale the value on 18 digits. One thing that we realize is that by doing that, you cannot express an amount that is smaller than this number, right? So 10 power of 6 on Kusama, for example. And for that, we pushed a fix to the palette not too long ago, where basically we take one plank from your account and store like some dust amount in the palette itself. If you are trying to manipulate, if you have some transactions that are trading numbers that are lower than this number here. All right, address mapping. So On most substrate chain, we are using account ID 32 for the account address. Usually your account in Polkadot wallet is represented with like this SS58 encoding format. And we look like this. Whereas on Ethereum, we are using 20-byte long addresses. So the type that is used for it is H160 for 160 bits. And usually, like, addresses are represented just by their hexadecimal format. So to deal with this, we have another type called address mapper that has like these three functions here. You have a function to address to go from an account ID, so most of the time account ID 32 to an Ethereum address. You have the reverse to account ID to go from the address to an account ID. And finally, you have a function map to map an account ID to an H160 address. When we do that, we use kcac to take the hash of your 32 bytes, and we take the 20 last bytes of these 32 bytes to create your address. And because it's a lossy process, right, to hash your 32-byte address, we have to keep that in a storage map to do like the reverse lookup, right, to go from the 20 bytes to the 32 bytes. So if we take a look at this in action, there are two scenarios basically. Either you have an Ethereum wallet and an Ethereum, private key, in which case you will have like a 20-byte address, like Alice here. When the pallet needs to access the account ID that is mapped to this address, it will call to account ID. And the way it's doing that is by suffixing your 20-byte with EEEE at the end. And then when you want to convert this back, the true address basically like just strip out like the EEE suffix. So it's kind of a cheap operation. If you have on the other side, if you're like if you have a Polkadot wallet and you start interacting with the pallet with an account ID 32, so you'll have like an address like Bob here. And so when you call to address, it will take the 20-byte address, and as I said, like kcac, hash it and take the last 20 bytes. And of course, if you do that without any kind of storage and you call to account ID, you won't be able to restore like the initial address, right? So that's for that reason that we have like this map extrinsic, which you have to call once. And that is going to set like this stateful mapping. And once you do that, like the address mapper will use like this storage, and it will be able to convert it back. So ideally, Polkadot wallets, that want to interact with contract are aware of this mapping and will do like this one-off operation like once, so that it's transparent for the user and it's it doesn't hurt too much like the user experience. All right. Yeah. Then the gas model. So things here are also like a bit different. On Ethereum, every opcode cost is defined either in the initial like yellow paper or in subsequent EIPs for the forks that have been different forks that have been created on Ethereum. In Polkadot, things are, on our implementation, like we don't use, the yellow paper cost. Instead, we benchmark all of the host functions that your contract can access. So just like in any of your frame palette, we have benchmark for each and every one of these functions. So that means that as you improve like the spec of your reference hardware. So let's say tomorrow we want to deploy that on Asset Hub, and we want to bump the specs of the collator on Asset Hub and give it like a much better hard drive, for example, which is much faster. Then we will rerun all these benchmarks, and as a result, the cost of all of this operation will be much cheaper, right? On Ethereum, you can't really do that, right? Like the only knob that you have is update like the gas price, right? Everything else must follow like what's defined in the spec. Another thing is that on Ethereum, like there's a quadratic memory expansion cost. So every time you want to allocate more memory, it will cost you quadratically more. And that's so that you don't run out of memory, right? Eventually, you will run out of gas before you run out of memory. Basically, that's the model used in Ethereum. We think that the gas should be a representation of like the compute time, not the memory, right? So in a sense, it doesn't make much sense to charge them more for the memory. So on Polkadot, on Palette Revive, we use like a fixed memory expansion cost, right? We have hard limits that are defined, but every expansion costs the same price. I mean, it doesn't cost you more. Yeah, so we have like all of these hard limits that are defined that we have bumped recently. So there should be like this should be high enough by now to execute any kind of contract that are already deployed on Ethereum. For example, our call stack is limited to like 25, so you can go 25 contract down, which I think is more than enough. All right, and then the hardest problem that we have to solve is like the problem of gas mapping. So on Ethereum, you have like a single unit of gas, right? You have like a single number, the gas that is U64 that define your gas. On Palette Revive, because we are on substrate, we use weight, and we have also like a storage deposit, right? Because we think we should not conflate the disk space again with like the compute time. So why do we have weight? Because so the weight, if you are not aware, is defined as two components. You have the ref time, which is kind of the equivalent of like the Ethereum gas, like the compute time. And then because we are operating on a sharded network, we have like the POV. Every storage that you access, not only in Palette Revive, but in every palette, need to be recorded in a proof, because when your call is going to be verified by the proof of validity function on the validator are stateless, and so they don't have access to the storage, and so they need to read like these storage keys and values from like the proof that you have built. So for that reason, we have like the POV. Yeah. So yeah, gas mapping is a complex topic that we are still finalizing. What did I want to say here? Yeah, on Ethereum, they also conflate like the storage deposit with gas, right? We think it's not the right approach, because one could create like a lot of storage when there are like in a period of low congestion on the chain, and you will end up with like a chain like Ethereum that is a bit bloated with all of this disk space that has been used later on. And at the beginning, I think they fixed that in follow-up EIPs, but you could have some trick like that where you will create storage when it's cheap and then remove it to get the refund later on. The other complicated thing is that Ethereum is expecting that the gas multiplied by the gas price is represent exactly like the fees that that you pay. So if you look at Block Explorer, I mean, if you look at the receipt of an Ethereum transaction, there is no fee field, right? The fee is implied by multiplying these two values. So On the current solution that we have implemented, we have what we are doing is basically we estimate like the call, and then we encode on the lowest digits of the gas value with a lower precision these three dimensional gas parameters. So like the ref time, the POV, and the deposit. What we do is we take like the binary roots of the actual values and we push that into like the lowest digits, so that when we execute the transaction, we can restore these values and pay for the pre-dispatch rate of the call. This is kind of like the simplest way of doing things, but unfortunately, it's a bit brittle. And the reason is that some wallets and some dApp as well are going to bump the gas estimate that is returned by the RPC, right? They're going to maybe bump it by 10%. And because we don't have a linear mapping, if you bump like this, the value that is returned, you're going to mess up with like this values that we have encoded in the lowest digits, and your code is going to break. So that's not great. So we are currently like fixing this with another approach that is still being finalized. I won't bother you with all the details, but basically the idea is that we're going to map the fees that you paid is basically as like a fixed ratio between like the POV and the ref time that is defined in the pallet transaction payment. And we're going to use the same ratio to like define how like the weight breaks down between these two. And so we will have like linear mapping between the gas and the weight, and we'll be, if you add 10% more to this value, it will mean that you are consuming like 10% more of resources. So that's still being worked on. It's not it's at the stage where we are just writing design doc, but hopefully it will land soon on our palette.